Hello, good morning, everyone. Hello, could you please let me know if you hear me well?
Yes, we can.
Wonderful. Wonderful, great. I'm starting my virtual whiteboard and we're going on in a minute. Good morning once again. We will have a little bit shorter lecture today because I have another meeting at 10. So we have just 1 hour, okay? So first of all, as discussed and as decided, we'll have our midterm next. Well, that's the question. You have labs on Tuesdays and Thursdays, right? Or Wednesday and Thursday?
Yes.
Which way? Tuesday, Thursday, or Wednesday, Thursday?
Wednesday, Thursday.
Ah, okay, it is Wednesday, Thursday. Okay, never mind. What we'll do, we'll have, nevertheless, I was originally planning to do it on, instead of a lab, actually. But never mind, we'll do it as a part of our lecture on next Tuesday. So there will be midterm. Nothing really difficult is expected. So there will be some generic questions about our setup, our data, our main principles. So for example, there could be questions about what happens to the order book if a certain order comes in, or if, let's say, a certain order is deleted, or if an aggressor of whatever size aggresses the bid-ask spread, or about the statistics we are dealing with, about how we normalize the data, about the principal tasks of data mining in general. So, for example, data normalization, cleanup, abnormality detection, and things like that, based on not just any abstract questions. How do you detect, let's say, outliers, but how you detect outliers in the setup we are working with. So things like that. Everything will be tied to our subject domain. Okay. So if you attend the lectures and if you do the labs, I don't expect anything difficult at all regarding this. Okay. So don't worry much about that. Now, as you see, our view of data mining, and we have discussed it in the very first lecture. We discussed what data mining is all about, what are the tasks and objectives of data mining, and our view of this is based on a particular subject domain. So our subject domain is a microstructure of financial markets from the data mining point of view, all right? And I believe that it is a very good example because we can, first of all, learn quite a lot of things not just in any abstract way, just construct a distribution where our data items are denoted as xi, let's say. No, we know precisely that xi is an order book spectrum which we have constructed in this particular case, and we know what the ultimate objective is. So last time we have already started the order book spectrum and the Kolmogorov-Smirnov criterion for similarity or otherwise dissimilarity of distributions, right? So today we will continue on distributions and another important quantity which is called market pressure. And by the end of either today or maybe with some concluding remarks tomorrow's session, what do you think are we going to get? So we have already got this normalized order book imbalance. We'll study some other related characteristics today. What do you think we are getting out of that and why we are doing all that? So, okay, we construct one distribution, we construct another distribution, we normalize. So then what? We're at the halfway of our data mining course. All those characteristics, well, not all of them, but many of them we already know, and we're going to complete this in 1 or 2 days. So what are we going to do with them? Is it just for the sake of the exercise? Let's say compute the normalized order book spectrum. And what? What do you think we are going to do with it then? If anything. Or it is just for the sake of the exercise?
Compare them, like compare that change in the spectrums.
Compare them. So there are some things we can do. For example, detection of abnormal, some abnormal activities. Okay. Anything else we can do? Eventually, you remember the pipeline of data processing in the first. Let me draw it up. The pipeline, which we discussed in the very first lecture, the very first box is data acquisition, right? Okay, or let's say collection. Okay, great. Then really comes collection and maybe storage in raw formats. Okay. Then comes essentially our part. What we are doing here, data mining. And as we know, data mining is cleanup in no particular order because all these tasks are interrelated. So for example, if cleanup is one of the major tasks of data mining, with our order book data, how do we do cleanup? What do we do to that end?
So we filled order books and compare with orders of this day for this instrument and find some abnormalities, some wrong orders or wrong deletion, for example, because of the order book construction.
Yes, you are right. So in this particular case, cleanup occurs naturally as a result of order book construction. I would say that by order book construction, because when we construct order books, then we can really, in this data representation, detect abnormalities such as B-dust collisions. You remember we do a cleanup in that case. We can detect situations like, for example, we would like to remove an order and this gives a negative total quantity at a particular price level, so we zero it out and we remove it. Or an attempt to delete a non-existing order. So all integrity violations in order book construction are one way or another resolved, correct? That's what you have done, resolved integrity violations. And by resolving the integrity violations, you effectively achieve the data cleanup. Also, what else? For example, outliers detection. First of all, it is also done sometimes by order book construction. So, for example, an order which would not belong to the bid side because it is above, above let's say, the minimum ask is naturally removed in that case, but also outliers detection is done and can be done by means of what we are doing now, computing the descriptive statistics and comparing the distributions using, for example, the Kolmogorov-Smirnov criterion. In this case, these are not really outliers, but this could be illegally or unethically placed orders. Uh, so another thing is descriptive statistics. That's what we have done precisely by order book spectrum. And outliers detection could be made using precisely this order book spectrum and applying Kolmogorov-Smirnov criterion. As you can see, obviously our data mining is closely related to mathematical statistics. Data normalization, of course, descriptive stats are constructed via normalization. That's effectively, plus something else, how we do our data mining stuff in the course of working with high frequency data. Also, we develop one path, reasonably efficient algorithms to deal with large amounts of data. I'm absolutely sure that when you started, for example, writing your Python programs to read and process the orders log and construct your order books out of them, and then Python is not that super efficient and you need your programs to run more or less smoothly, not on a supercomputer, but on your notebooks. So you had to pay some attention to data, to overall program efficiency consideration. So for example, reading all the data sequentially, preferably in one pass, rather than reading all the data in one go, placing them in memory, and then constructing all those data structures in memory, because that would be totally infeasible from the memory usage point of view on small computers. So dealing with large data sets. May I ask you in this connection, actually, the size of the data sets we are working with, did they present any particular problems to you? I mean, given your computational resources, normally you do it on your just personal notebooks. And how? So the algorithms, the Python ones, presumably you have developed, are they efficient enough to construct, let's say, order books, spectra, and so on in a reasonable time, or you need to wait for days for the tasks to be completed?
Normally, for me at least, the first code I write usually takes a lot, but with some tweaking and like memory management, I can make it like run like instead of, for example, 3 hours, it takes like 40 minutes or 20 minutes. Also, I use multi-process programming to make it even faster.
Very good. So let us put here, this is a very good example. So in the course of doing that, you have algorithms and data structures optimization, all right?
Yes.
Let me put it here. And what is very important, you have mentioned, this is a very good example, you do parallel processing. To speed this up. Very good. So all this really belongs to our subject area, which is data mining. But these are only, I would say, the first half of our steps to be taken. So what do we do next? So we draw up, we can do more here. We will do a little bit more about descriptive statistics today and tomorrow. But what is our overall objective? So I am drawing up an arrow going to the right from this block, although it may naturally still belong to data mining, or it may belong already to the next step. So this is an intersection area between data mining and some subsequent analysis we're going to do. So what is going to happen here? What is it all for?
Like prediction and inference to learn something from the data.
Indeed, and the keyword here is to learn. So the next step is really part of more, well, it is a border area between data mining, data science. Data mining, as we discussed in the first lecture, is more part of data engineering. Data science is really science. But this border area between data mining and data science, we will definitely cover. So the next step would be to run some machine learning on our data. And the tasks for our machine learning would be, what are the tasks for our machine learning? The tasks will be really some short-term price prediction. Plus maybe something else, but this short-term price prediction is probably the most important thing to do. Short-term would probably...
I wanted to ask a question.
Yes, please.
Sorry, I wanted to ask a question about that. For like high frequency trading, is it like feasible to run like something like that, like a model that predicts the next price for like the last 2 seconds data or like last 10 seconds? Like, is it doable, or like does someone do it?
So first of all, you are completely correct in identifying the horizon for this prediction. So you're absolutely right that you are talking about the interval maybe of 1 to 10 seconds. Something
Yeah, so
like
is it actually doable? Like,
yes.
Is there someone that offered the data to do that?
And you know what? Not only it is doable, but we will try to do it based on the data we have. more successfully or less successfully, but we'll lay down the foundations which allow us to do precisely this kind of task. And obviously, predictions for longer periods of time are very difficult. They would require analysis of longer term factors, which may not even need to take into account the market microstructure in that, to that extent. But 1 to 10 seconds prediction, let's say on the minute prediction, is definitely microstructural one. I can tell you the following. So on the time scale, let's say this is our A0. So if our interval is, let's say, intraminute, and we'll now see why. If our time scale is intraminute, so 1 minute is here, then it is really microstructure based, and microstructure is what we're studying. Microstructure based analysis and prediction. From, let's say, minutes on, it could be 1 minute, it could be 5 minutes, somewhere from this point on, it is probably slightly, it is not already microstructure based, but it can be based on all prediction is statistical. Microstructure based prediction is statistical as well. But this is based on more classical form of, let's say, stochastic differential equations, which are commonly found in quantitative finance. Why the difference between the two? Differential equations. Let us see. If we consider this area, then the main, I would say, point, the main instrument used here to model the stochastic process and predict something, we do not predict the values, we predict the probabilities. We can predict, for example, that with the current market dynamics, we wouldn't say just we say that the price will go up, let's say in the next 10 minutes, but we can say the probability that the price would be maybe, let's say, 0.1 ruble for USD ruble higher than now at some moment between now and 10 minutes is 70%. That's a kind of predictions we are making using the stochastical methods. And similar probabilistic predictions we are going to make here, only the mathematical machinery is different. Here it is mostly machine learning. Here it is mostly stochastic differential equations, SDEs. And how to distinguish between these two modes, and why, for example, stochastic differential equations are not applicable to very short periods of time. There is a very basic building block for analysis, which is used here, which is a so-called Brownian motion. And this is just a normally distributed process. Let me denote it by W. It depends on time, and it has a normal distribution with zero mean, and the standard deviation being square root of time. What does it mean? If you know that the process started, for example, from 0, that's our building block, then it is very close to 0 anyway, it is continuous for small time, but then it can go anywhere up and down. So its standard deviation is small here, it is larger here, it is even larger here, it is even larger here, and so on. And in general, the standard deviation is increasing at the square root of time. And microstructure-based effects, which we are studying here, they arguably, we are arguing now as more physicists even than data scientists, just when there are two physical theories and we're arguing about their applicability. Where does it happen? It happens when the price effect of this stochastic Brownian motion movement, it is comparable with B-dusk spread. And now it is relatively easy to say how it happens actually. You remember, so did you measure the typical B-dusk spread? I was telling you that it is about 1.5 copics, for example, but did you measure it on your data? Can you tell me, for example, I measured the time average of B-dusk spread and TTP to be that one. If not, we will have to do it. So B-dusk spread is yet another very important parameter which will be actually fed here. So the parameters which we are feeding into our machine learning is order book spectrum. That's the first thing. That's number one. Number two, B-dusk spread, and so on. We'll learn about others soon. Suppose that B-dusk spread, I denoted by delta S, is this 0.015, for example. And the price S itself, let's say for USD ruble, is, let's say, 75. Then we can have from the stochastic process point of view the following relationship. Delta S divided by S, a relative one. So this is a relative accuracy to which we can get our model if we are here in the right-hand modeling. So delta S over S would be some proportionality coefficient sigma, which is called volatility, times this absolute value of delta of Wt, which is proportional to the square root of t. So very approximately, I can say delta S of S is some kind of sigma times square root of t. Sigma, if t is measured, and in finance, interestingly, we measure, of course, it in seconds and microseconds, but when we work in this right-hand side model, currently we're working here, but if we work here, then t is measured, strangely enough, in years. And in this case, we can see that t is simply delta S over S divided by sigma squared, right, in years. And if we want it in seconds, in years, and t in seconds would be delta S over S times sigma squared multiplied by the number of seconds in a year, which is 31 million. So times 31, approximately, of course, 10 to power 6. So please compute. What do we get here? So suppose that delta S is about the B-dusk spread, 0.015. S is 70. We need a value for sigma. And this is so-called volatility of the effects process. And I can tell you that a reasonable value for volatility is, for example, again, 0.15, 15% a year. Then what? Delta S over sigma is precisely 1/10, and therefore t seconds is something like 1 divided by 750, because it is 1 over 10 squared, times 31 10 to 6. Please compute what it is going to be. I believe that it is about 1 minute indeed, so it is probably just 58 seconds or something like this. Please compute. Let's take a calculator, and we say 31 million divided by 750 squared. Yes, it is 55 seconds. So you see why we are doing this. So this is approximately 1 minute. And this justifies what we have wrote here. So this is a very much, you studied physics, right, at Innopolis. So you know that there are classical mechanics models and there are quantum mechanics models. And there is a certain, I would say, area of applicability for both. So there is a certain barrier uh, which distinguishes between classical and quantum mechanics. Very similar story happens here. Our very, very approximate computation has shown that indeed this 1 minute is a kind of threshold, and under 1 minute it is precisely the microstructural effects, and after 1 minute it is about stochastic differential equations effect. So based on our microstructure machine learning, we can indeed hope to provide continuous price prediction for, let's say, interminute rate. Nice example, isn't it? We really quantified this estimate y interminute. Okay? By the way, is it more or less understandable
Okay.
what we have done here? I think it is very instructive. But now I can ask you the following. Okay, suppose that we then develop, and that's what we're indeed going to do in the second part of the course. We develop machine learning algorithms which allow us to provide intra-minute continuous price prediction. So based on all the stuff we're receiving, we can probabilistically, of course, again, not precisely, but probabilistically tell what happens with our price within a minute. How we can use this information. So, in practice, in real life algo trading. So yes, suppose such predictor does exist. We'll construct it eventually. So let's think what this predictor will do. The predictor, what do you think? What kind of predictions can we expect from this predictor?
We can make like something, a regression model that give us like a linear prediction, something like linear regression.
Yes, this is definitely one of the first steps we'll follow. And actually, as I probably mentioned in the first lecture, you are absolutely right. The most important thing is to do the right feature engineering. If feature engineering, what we are doing, for example, normalized spectra, other features, BDASK spread, and so on, which we are going to put into our model, if the features are engineered correctly, then the complexity of the model itself is of less importance. With correctly engineered features, even a linear regression model, as you correctly pointed out, can yield meaningful results, and it may or may not be necessary to go for deep nonlinear models, such as, for example, what you learned from your machine learning course you previously attended, like neural nets, support vector machines, and so on. It may or may not be possible, and typically those large, possibly overfitted, even linear regression can be overfitted, models add not that much information. They do add something compared to simple linear regression if we constructed correct correct set of features. And if we didn't construct the correct set of features, then whatever complex model we do, it would be more confusing than useful. So what we are doing here at this stage, so you see these numbers 1, 2, and so on, we do really feature engineering for our subsequent machine learning tasks. So we do, this is precisely what we are doing. This is feature engineering. But my question was slightly different. Suppose that we do have this linear or otherwise predictor. So what kind of questions? Suppose that we are now at time t, which is notionally 0, and we have this price as 0. As you already know, the very notion of price needs to be defined. So suppose it is a midpoint. Suppose it is a midpoint. And suppose that the bid-ask spread is now delta S 0, which is our bid-ask spread. Something like this. And we even have the full spectrum at time 0, if we want. And so on. So we have this set of features. So what kind of questions do we ask to our prediction system? So, okay, this is t equal to 0. This is t equals to, let's say, 1 minute, no more than 1 minute. So what exactly our predictor can predict for 1 minute?
Delta 0.
Sorry?
The difference between midpoints of S0.
Okay.
Between two times.
So you see, that's a very important thing. We can, of course, simply build a regression model. So then there is some kind of ST. Let me even call it T capital. So it is about our threshold. So we wouldn't move beyond this. So, okay. Obviously, what you can do, you can do a regression model, for example, a linear or otherwise regression, which provides a regressed value of ST, right? So effectively, what this model will provide, what is a regression? In statistical terms, this is the expected value of ST. So our regression model, if we build it, regression model, ST itself is a random variable when viewed from S0, so we don't know this value. But a regression model will provide us with some kind of ST hat, which is effectively the expected value of the real ST conditioned on, let's say, S0 and other features, which we know at time 0. All right? So basically we have S0 and other features, and this allows us to estimate the expected value of ST. And this is our ST hat, and that's what regression will give us. Would you agree with that? We can't say that the regression model will give us the true value of ST. Of course not. Whatever regression we do yields only the expected value, right? Please just
Yes.
reflect on this. Do you agree with this statement?
Yes.
Okay. But then my second question is it really all we want? We may want a different kind of information. So suppose that, why just a regressed value? We can do better than that. We can even try to, although it might be difficult, but we can try to, in some very, let's say, rough terms, but nevertheless, we can try to construct the distribution of ST is a random variable, based on the information. Let me denote by, let's say, F0 from the information theory point of view, all information available at time t0, which we constructed into features. And that's why F0 is the set of features which we have. Okay? All infra as features available at t equal to 0. You know, this set of features, let me put it that way. We have quite a lot of features, right? So, for example, the order book spectrum, which is more than just one feature. The spectrum consists of 10 bands on the bid side, 10 values on the ask side. So it's already some kind of 20 values, plus bid ask spread, plus something else. So altogether, we would have about, let's say, several dozens of features. And if using these several dozens of features, we just construct a single regressed value, this ST hat, we are probably underusing our information. So we convert a relatively rich feature set F0 into just a single number, ST hat. Correct? I think we can do better than that. Why should we convert, let's say, 40 features into just one expressed one regressed value? Moreover, we can also, for t equal to 0, we can also take into account features like the previous history, prehistory. So not necessarily what happens at t equal to 0, but maybe some snapshots, maybe spectral snapshots corresponding to t less than 0, so several steps into the negative. And that's, by the way, the principal difference between these two regimes. Let me return into this picture. If we are in this 1 minute plus area, then with the model based generally on Brownian motion, we can say that the previous history is typically irrelevant. This is called Markovian property. Whereas under 1 minute, positive or negative correlations between our features do play a significant role. So here we would say history matters, obviously short term. History matters. Here, at least for the Brownian motion itself is a Markovian process, which totally forget the history. It doesn't mean that the history is totally irrelevant, because apart from the Brownian motion, there could be some trends and so on. But for the Brownian motion itself, the history does not matter at all. But when we are here in the interminute region, the history is important. So we may build a relatively rich feature set. And from this feature set, I would say it would be pity to get only the regressed value. What else can we do? We can build, so a regression model is number one, but more important than that, we can build, let's say, the whole forward distribution of our price at ST. Why forward? Because it is estimated. Forward estimated distribution of ST, where, by the way, S0 was a midpoint, therefore ST is midpoint as well. So we can say the probability, and we'll be able to then answer questions like that. What is the probability, let's say, of ST being greater than S0 plus delta, where delta is a certain, let's say, threshold? Based on this forward distribution, we'll be able to answer questions like this. Or, without building forward distributions, we can, for example, fix delta, and using again some kind of predictive or regression or whatever models, we would still be able to answer questions like this. Let's say, or probability that ST is less than S0 minus delta. Why do you think these questions which are marked with 2A important? Very important.
They can give us the CDF of the distribution.
Well, not only that, we can use, if we have these probabilities, then we can use them as direct trading signals. So this is not just an abstract data mining. This is algo trading then. So you were asking whether we can make predictions, for example, within the under minute, interminute range, so that they could be meaningful for real life trading. Yes, that's a kind of signals. So I would say that 2 and 2A are by far more important signal than 1. If we only estimate the expected value, this is not that much information. Okay, we estimated the expected value, but what if the standard deviation around this expected value is big? So although expected value is regressed, then we don't know the probability of being, for example, below or above this expected value. So we don't really know how this our price would behave at ST. But if, for example, we put, I don't know, delta to be 0.2 rubles, for example, we put t to be 1 minute, and indeed our model, which was inferred from our data, said that the probability of ST being greater than the current price plus 20 kopecks is significant. So, for example, this probability appeared to be, I don't know, 70%. Then this tells us something. So this probably tells us that we should enter a long position, which means buy USD, because the price is increasing. If, on the other hand, the second probability is about 70% that ST is going to be less than S0 minus delta, then it probably strongly suggests that the price is falling and we should take enter a short position. I would say enter a long or short position, so buy or sell our USD, which is easier to say than to implement, but nevertheless it is a real signal. So not just a mathematical model, but it is a real life trading signal. Would you agree with that?
Yes.
Yes. And now we can do even more than that. Why should we really be interested in the distribution of our price at T capital? So for example, if our trading signal is intended to, for example, enter a long or short position, then imagine the following situation. So that was S0, then the price oscillated somehow, and then it arrived at T capital. So for us, and we put this threshold delta somewhere. So that's delta. So for us, it is less important where the price is going to be, I mean, in the probabilistic sense, exactly at T capital. For us, it is important whether it will cross the delta level at 0 plus delta. And similarly, we can put a barrier at 0 minus delta, okay? Whether it is going to cross the threshold at some point, let's say tau, in between zero and between 0 and T capital. If it crossed the threshold already here, then by buying at time 0 and selling at time delta, we can already make our delta profit, correct? So,
Yes.
so in fact, we would be interested in questions not only of that kind, but probably to be probability not of ST being greater, that there exists tau in the interval from 0 to T capital such that S tau is greater than S0 plus delta, or maybe probability that there exists tau, let me write it in short, there exists tau in the interval from 0 to T such that S tau is less than S0 minus delta. That's what we are probably going to be asking about. But how big delta could be? We already know from the information available that, for example, T being of the scale of 1 minute corresponds to, let's say, natural volatility of prices from the Brownian motion consideration at the boundary at about 1 minute of prices to be of the order of bid-ask spread. So basically, when we are interminute, then our prices move either way only for the size of the bid-ask spread, correct? On average. Maybe at some points a very strong order book imbalance, which we realize due to the spectrum, would give us, for example, a movement of two bid-ask spread. So if bid-ask spread is delta S, typically, then the price would precisely move, let's say, 1 to delta S within this interval. And then the question is, okay, Suppose that we have implemented our predictor, all is fine. It works. A probabilistic predictor works. This kind of probability estimation works, and this is actually a very good outcome which we can get from our machine learning model. Suppose that, I fully agree. What then? How can we make practical trading use of this information? Why it is difficult? Okay, suppose that we have this prediction even for two deltas. In order to use it, we first buy at T0 a certain number of dollars by firing up at T equal to 0. We fire up, let's say, in order to buy, aggressive buy. We do it, not anyone else. We do it because our prediction has shown it. Aggressive buy, and at T equal to, not necessarily T capital, at T equal to Tor, within this interval from 0 to T, we fire up an aggressive sell. You remember our discussion that when you fire up an aggressive order, you effectively spend half of bid-ask spread. So you immediately pay delta S, so compared to execution price at midpoint. So basically, you immediately get a notional loss of delta S, minus delta S here. And yet another one when we do it aggressively once again, minus delta S. So even if our prediction is correct, you earn this quantity, 1 or 2 delta S, and you spend delta S. So effectively, with this aggressive strategy, your PNL, or profit and loss, is going to be, let's say, 0, 1 delta S, depending on the size delta you are targeting. And obviously, in most cases, it would be 0. In some rare cases, if you successfully predicted, for example, a movement for delta being greater than, for example, 2 times delta n, then you realize eventually 1 delta s PNL. You know what? It is not infeasible. This kind of strategy might be viable, and even by itself, if our machine learning model, not in the ST regression sense, but in this probabilistic sense, if this model is implemented, it can work. But we can do better than that. We can do better than that by passive execution without firing up aggressive orders, but instead acting as market makers and placing passive orders. What if MM type strategy is used? Based on passive orders. We will discuss it when we continue tomorrow.
Just a last question. If we use market maker strategy, we are still paying the first half delta S because we need to buy now, but then we can sell later with the market maker.
That's a challenge. That's a challenge. So we will need to consider it more detail. Let us just wait until tomorrow until we'll cover a market making strategy, which would still benefit very much from this type of probabilistic predictions. And it may even make things better because we are not spending bid-ask spread in that case. So let's wait until tomorrow, and then we'll set up perhaps the problem for our machine learning, which we will aiming at in order to implement a profitable trading strategy. We are done for today because I'm running for another meeting in a minute. Thank you very much for the attention, and tomorrow we'll continue from this point on. Okay?
Thank you.
Thank you. Thanks.
Goodbye.
Bye.